Hi, very good morning, good afternoon, good evening. Okay, so this is gonna be that extension of or that continuation of what we had been doing on last Thursday during our last class session. So we were talking about we were at the last chapter of that particular class in which that we were talking about that chapter 7. We were covering the material in chapter 7. So I was in the middle of that covering the material, and then we were talking about the effect size. Can you remember that in this particular discussion, we had a new variable being added to that our model, which is a categorical variable, has been added to our model, and that we was uh, just checking and then studying that how this explanatory variable, which is a categorical variable, gonna affect to the response or the outcome variable, which is a quantitative variable. And we were studying that one, how they were related, and then how this categorical variable going to affect to the other variable. And then this effectiveness, effectiveness can be that easily calculated by several ways, and then that we were talking about can be evaluated or calculated in a different ways. And we were talking about that one, and then when we stopped the last class session. So today we're going to pick up from there. You can remember that we were talking about the effect size, how effective that this given model would be. For that particular discussion that we built up, we were at the 7.7 measures of effectiveness. What I'm going to do, I'm going to go ahead and then share my other screen. Okay. Yeah, this is where I stopped last time. So far we have been talking a lot about the model using sex as the explanatory variable. The sex model is an example of what we could call a two-group model. It can be called that one either two-group model or sex model or categorical model. Okay, because there are two values of sex in this data set and thus two group of data. We've been thinking about trying to measure how good or bad our model is, but there's another way to think about this one. Given that the explanatory variable x with an effect of an outcome variable, the thumb length, how big is this effect? We call the answer to this question effect size. We haven't used the term effect size up to now, but we have in fact presented two measures of the effect size so far. You can remember the mean difference. The mean difference, also known as B1. The most straightforward measure of the effect size in the context of two-group model is simply the actual difference in means between the two groups. See, that's the actual difference in means. Okay, it means between two groups on the outcome variable. See, you are looking for the actual difference in means. See, actual means between two groups on the outcome variable. These are the parameter estimate for the sex model. Which number shows you the difference in means on the thumb lengths between two groups? Difference in means on thumb lengths, okay, or the thumb lengths means for male and female, okay, will be shown by which number? See, this is B1. This is B1, 6.44. This is B0. That's the average or the mean value of the females, okay. So this is the difference in means on thumb lengths between two groups. Okay. So this one is 6.4. In our data set fingers, we can see that the size of the sex effect is 6.44 so millimeter males. On average, have thumbs that are 6.447 longer than for females. See, the males on average have thumb lengths 6.447 millimeters longer than females. That's what it means. So this has been rounded to one decimal place, 6.4. Anyhow, that this is the difference mean on the thumb lengths between two groups. Okay. Then there's another one. The B1 how is as you can take as like a function. instead of just go to this run the function and then get B1, yes, you can get the B1 through the function, see, through this model, see, thumb, sex, data, like that. That would give you the value of B1 as well. See, B1 is a function. It will return 6.44, this one, pretty much the same one, see. In addition to that one, we can talk about the pre. Pre is that the second measure of the effect size, as we just it tells us the proportional reduction in error of the two groups over the empty model. See how much error has been reduced due to this the new model. See, that's why they say that the proportional reduction in error of the two groups model over the empty model due to this new model. It will talk about that reduction in error of the two group model. See, reduction in error of the two group model over the empty model. So you're going to talk about two models being compared and contrasted. So you are talking about the how much of the error has been reduced due to, okay, or due to this new group over the empty model. Pre is a nice measure of the effect size because it is relative. It is a measure of improvement, reduction in error. Improvement like a reduction in error that results from adding in the explanatory variable. But what count as good pre? Recall that tiny sex model had a pre of 0.66 while the sex model had a pre of 0.11. Are pre in general going to be as large as tiny sex model? Probably not. In the tiny fingers, we stack the deck for purposes of teaching, creating a data set in which all the females had smaller thumbs and all the males. This resulted in a large pre. See, that's resulted in a large pre. As with every other statistics, pre will vary from model to model and situation to situation. Having more experience with the making models will give you a sense of what count as an impressive pre in your research area. See. In the social sciences, at least, there are some generally agreed on ideas about what is considered a strong effect. A pre of 0.25 is considered a pretty large effect. See? If pre is 0.25, is considered to be a pretty large effect. 0.09 is considered a medium effect. And 0.01 is considered to be a small effect. So, according to these conventions, there's a medium effect of sex on thumb length in the finger data set, because in the finger data set, if you go ahead and look at this threshold value for the pre, is a see pre has been so I'm gonna get this one here. See pre pre. So proportional pre means proportional error in the two group or sex model or with the empty or null model. Okay, null model. So that how could we gonna be that this particular model would be a better model by looking at what if pre is around like a 0.25, pretty large. Say pretty large effect size. is 0.09, we can say that medium effect size. If it is 0.01, so it's going to consider as like a small effect size. Small effect size. See, these are the values there. These are the threshold value: 0.25, 0.25, 0.09, and 0.01. Okay. So therefore, in that fingers data set, the sex on the thumb length is a medium effect. There's a medium effect. Like for instance, example, see, in fingers data, sex or gender has a medium. PR is like a 0.11. See, effect on thumb length. See, thumb length. It's a medium effect. See. Even for the PRE, you can just by running PRE, you can easily get that one. See, similar to B1 function, PRE function will return the PRE for a model. In the data camp window below, run supernova. And for this one, look in the supernova table to see what the PRE is for the sex model first. Okay, let's run this one and see what PRE would be for the fingers data. Okay, 0.11. Okay. So then what we're going to now change the code to run the pre. See, instead of that one, instead of LM, you can just straight go and then run here. See, or like this. Or since it's already run, PRE of sex model. See, sex dot model. Has been saved to this object. Therefore, either way, you get the same answer. See, now the third measure of effect size called the coherence D. The third measure of effect size that applies especially to the two-group model, such as sex model, in coherence D is related to the z-score. Recall that z-score tells us how far an individual score is away from the mean distribution in standard units, okay, standard deviation units. So that the difference between that one, but similar fashion, you can remember in the z-score, you were talking about how far that given, see, given that particular data point is how far y minus y bar divided by s. Now the coherence D is denoted by simple D, okay? Coherence D is nothing but y1 female minus y bar male over s. Like that. This one if you want for the male, that's for the male. If you want for the female, then y male, y female, y bar female over s female. This one is male. See? So that if you wanted that z-score for the males, then you can say that observation of the males minus the its mean value divided by Sm, and pretty much similar fashion you can write the same thing for the female. What this means that given any data point, data observation is how far that given observation in terms of its own standard deviation. This time we have the difference between their means in terms of the standard deviation. This standard deviation would be whether it's going to be female or male. No, none of them. It's a combination, it's a combo, it's a pooled one. It's neither this one nor that one, but that's the pooled one. That means that this is standard deviation for the all of them. This is standard deviation for the all of them. This is standard deviation for y. See, I can put like that. That's a standard deviation for y. See, so the standard deviation of y you can calculate in another way. This way, or you can simply use y bar f minus y bar m deviation by the root mean squared error. You can remember root mean squared is nothing but y bar f minus y bar m over, okay, see, root mean squared means square root on mean squared error. So you can remember mean squared error. See, you can use that absolute value for this one. See, you can use the absolute value. See, mean squared error. See, you can standard deviation. That's why they say, see, this one. If you try to calculate coherence D, you will soon encounter question, which standard deviation should you use? The standard deviation of the outcome variable for the whole sample. See, outcome variable for the whole sample, or the standard deviation of outcome variable within the two groups. If the group means are far apart, if the two group means are, the standard deviation for the whole sample might be considerably larger than the standard deviation within each of the groups. See, you know that the overall standard deviation is far away from the individual groups standard deviation if they were so, see, variables within the two groups. If the two means are far apart, the standard deviation, if the two means are far apart, then the deviation of the standard deviation for the whole sample might be considerably larger than the standard deviation within each of the groups. In general, we will use the standard deviation within groups when calculating coherence D within groups, because this is the best estimate of the variation in outcome. That is not accounted by our model. But because the standard deviation will often differ from group to group, we need a way of combining these two groups. See, one possibility is just to average the two standard deviation. This works fine if the two groups are the same size. But imagine a situation where the sample size in one group is 100, but in the other only 10. If we average two standard deviation, we are assigning the same importance to the estimated standard deviation based on the group of 10 as to the estimate based on the group of 100, which doesn't seem right. We should have more confidence in the estimate based on the large sample. The solution is to use the weighted average of the two standard deviation, weighted by the number of degrees of freedom in each group. This is often referred to as the pool standard deviation, and this is what we use to calculate. We calculate to use to calculate hence D. The pool standard deviation is calculated like this way. Okay. Another way to find the pool standard deviation is to simply take the square root of the mean square error on your supernova table. See, pool standard deviation is to simply take the square root of the mean square error on your supernova table. Mean square error, recall, is simply the sum of squared error divided by the degrees of freedom for error, which yields a variance estimated only on the variation within groups. See? Only on the variation within groups. See? So that way, instead, as I mentioned over there, this can be easily calculated with the root mean squared error. See? Root mean squared error. Hence D. Hence D. Okay. Hence D. Hence D. Okay. Effect size is given by hence dm. It's being contrasted with the c-score. So you can use the mean squared error, or you can use for the coherence D. You can use y minus y bar mere over something called S pool. S pool, where S pool is nothing but weighted standard deviation of groups by the by their respective degrees of freedoms. That means you go to S of male, degrees of freedom of male, plus degrees of freedom of female and S of female, divided by degrees of freedom of male plus degrees of freedom of female. In weighted by the degrees of freedom of each group. Then just simply add. When sample sizes of the two groups are different. Okay, that's another way to do it. So another way to do that on Cohen's d is y bar f minus y bar m divided by s. I would call the averages. See, I'm going to put bar. So where S bar is nothing but S mean, S of male, S of female divided by 2. It's not being weighted. See, when sample sizes of the two groups are the same, see, then you can use this one. See, then you can use this pool and this one. Another one. Okay. So this one is another one. See. Another one. See. So there are three ways that you can get this done. One is using RMSE, or the other one is using a pool. If you want to use the pool degrees of freedom, you know the degrees of freedom of each one. And then here, degrees of freedom of FM means number of size of this one female, number of females minus 1. Okay. You know that. That's how you get the degrees of freedom. See? In our discussion, if it is in tiny fingers or fingers, okay, based on that one, you can figure out how many, and then based on that one, you can get this done. See? So that means Cohen's d. See, you can get by y bar f minus y bar male divided by mean squared error or y bar f minus y bar m absolute root mean squared error. That's a one way. The other way, y bar f minus y bar m divided by s pool, which means y bar f minus y bar m over degrees of freedom of this guy times s of male, degrees of freedom of female, standard deviation of female divided by degrees of freedom of male plus degrees of freedom of female. Okay, that's another way to look at that one. Okay. And the third one, then you can say Nm not equals to Nf. The other one, y bar f minus y bar m over s bar. That means y bar f minus y bar m over sm plus sf divided by 2. See? So this one, sample size of male is same as the sample size of female. See? This one equals n female. See? So there are three ways you can use this formula. See? Either this formula, or this formula, or this formula. See? Three ways we can get this done. Or in that this one very easily you can use the Cohen D. See? Cohen's D. Cohen's D. They have that function to Cohen's D for that given model. See? See? It should produce this value 0.78. See? 78. See? That means that the difference between these two, that means in terms of the standard deviation. See? What is the unit in the number? This number has been expressed in units of standard deviations. Okay, standard deviation. We know that there is a 6.447 millimeter difference between the male and female thumb lengths on average. If you think about one standard deviation as a unit of measurement, then you can see that the observed 6.447 millimeter difference is little less than one of these standard deviation unit, 0.78 to be exact. With the see, then you can see that the observed this millimeter difference is little less than one of these standard, one of these standard deviation units. See, with something like thumb length, knowing there is about 6 millimeter difference is actually pretty meaningful, but for other variables such as Kragel and Small, clear what the straight point difference implies. Nevertheless, in both cases, it's somewhat illuminating to add the information from Cohen's due to the mix. Male thumbs are 0.78 standard deviation longer than female thumbs length. The standard deviation, see, that's what they say. Male thumbs are 0.78 standard deviation longer than female thumb length. See, that's how they're gonna do the physical interpretation in Cohen's D. Male's average length, or you can say simply the male thumbs length, are 0.78 standard deviation, not the millimeter, standard deviation longer. This has been given in terms of standard deviation, not the difference between their means. Their means are differ by this part. But we want to know that it's going to be expressed in terms of standard deviation. That's why I'm going to say that, let's see, illuminate this one, see. The male thumbs are 0.78, not millimeters, standard deviation longer than the female thumbs length. See? So match each measure of the effect size to the unit in which it's measured. Mean difference. See, that's the original. Pre, a percentage or proportion. Cohen's D, standard deviation. See? Different quantities have different units. If you take the mean difference has been expressed in terms of the given unit, millimeters. So different original units. But in pre, squared the percentage of proportion. It's a percentage of proportion pre. Cohen's D is in the unit of standard deviation. Okay. Extend into a three group. I mean, like the same discussion we can extend to a three group. Okay. You have now learned how to specify a model with the single categorical explanatory. See, single categorical explanatory variable. We have a single categorical explanatory variable consisting of two groups. Forget how we're going to say that. You have one categorical explanatory variable consisting of two groups. Okay. So we were talking about, see, so far we were talking about, see, so far we were talking about single. Single means one. Single, see, single, categorical. It's going to be categorical, explanatory, variable consisting of two groups, such as gender with male and female, males and females. See? So it's a single. See, gender is a one. It's not two. Single, and it's categorical. See? It's just single. It's categorical. Cat, and it's explanatory variable. See, explanatory variable. See, with two groups. So instead of these two groups, we can get a single categorical explanatory variable with three groups or four groups like that. Okay, that's what they are trying to do over here. It is actually pretty simple to extend this idea to categorical variable three groups. Let's use a new explanatory variable to explain variation in thumb length. Height, of course, height in our data set is a quantitative variable measured in inches. But let's make a new variable that turns height into a categorical variable with two groups, short and tall. We can do this easily now. Name the variable height two groups. See? We will use the entire function to cut quantitative variable up into groups, and then use head and select to look at the first 10 rows of the relevant variables. See? Fingers, height to groups, go to entire, go to fingers and get the height and divide this into two groups. And then we select, you get the two groups. See, the two groups are, see, if you go ahead and check that, they're going to call this one and 2 by default. I don't want to see by default 1 and 2. See, then you can call that one different way. Okay, you can call that one different way. Use the factor function to modify this variable so that is are labeled as short and number 2 are labeled as tall. Number ones are labeled as short, twos are labeled as tall. Just remember, use the larger data from fingers. See? So this is how you use the factor before. See? Fingers, go to 6. Go to 6, label 1 and 2, you take out like a 1 and 2, male and female. Then we say a fraction, you go over here, you got this one. See? And you're going to just copy and paste over here and let's change appropriately. Go to the, you need the height this time, not the sex. You need HID, height. Okay, then go to labels, which are now called 1 and 2. And for the labels, I don't need the labels 1 and 2. I need the labeled 1. I'm going to label as short, short. The number 2 being labeled as tall. Get rid of this one. I'm going to get rid of one of them. Then go to fingers, go to thumb, go to height two groups, then 10. See? See, let me see, C equals, close it, factor, okay, this one, but, okay, fingers, height to group, factor, fingers, height to group, see, for the height to group entire already, finger in height, okay, this one, 2, height 2, height to group, yeah, UP, group, then change that one and put it back into the same thing. Height to group, labels 1 and 2, label C, short and tall. fingers, copy, okay. Fingers, height to group entire fingers height to, they're gonna have like a fingers height GIGST to group level C1 to level head height to group. See, tall and short, tall and short. So we're gonna divide that into two parts and then make those default 1 and 2 being replaced by short and tall. See, 66, 70 height, thumb length. Now we have a height to group. See, using the same approach we used to sex, we can write the model height to group like this. See, same like that. Now instead of this one as a categorical variable, see, B0. See, now look at the B0, B1, X1. This is the height to group. So y ins for thumb, X would be height to group. Okay, I'm playing with this one, not with this one. Okay, not with this one. This is my Y, this is my X. Okay, X. See, go ahead and fit the height to group model and take a look at the parameter estimate. See, height to group model. How do you fit it? LM, excuse me, thumb, tilde, height to low UP, data. The name of the data name is thumb. No, not the thumb, sorry, fingers data. And then height to group, the LM thumb, height to group. And then last one, see. This is B0, sorry, this is B0. Those are the height, average height for short people. This is the difference between difference of that two heights in two groups. See, difference in heights in two groups. This is the difference in height in two groups, short and for. See, for 6 1. See. So B0 is this one, B1 is this one. We know for sure. Why does it say height to group tall in the output? Say this is the increment you add on for the thumb length of someone in the tall group. You add on the thumb length of someone in the tall group. See, you have to add this much for someone in the tall group to get this one for the people in the short group. You see, you're going to add this one to the tall group. See, increment. That's the increment you add on the thumb length. Thumb length in the tall group. If you have a thumb length in the tall group being added this much to the short people. Okay. How would X be coded in order for the model to make sense? 0 for short and the 1 for tall. See? See? So that means that this is that. See? So then instead of go and look for, this is what they were talking about. See? So here Y is nothing but thumb. Okay. Then X would be what? Height to group. Okay, height to group. So here we have a short people. It's a tall. So they have the average. So I can say Y bar short. Somewhere here Y bar tall. Okay. Sometimes you have a grand total. The grand sorry, grand average. See, so this gap is B1, and this one has been given. That's the Y B naught, which is B naught has been, see, in this case 57.818, 57.818, and B1 is how much, see, how much do you have to add, see, see, the increment you add on the thumb length for someone in the tall group to make it a tall group plus thumb length 4.601, 4.601, 4.601, see, 4.601. Not the height, okay, height to group, okay, it's been there now categorized. This is factors, group into factors, see. So therefore y bar t is nothing but, see, y bar t is nothing but, see, B naught plus B1. See, B naught is 57.818 plus 4.601. So that would be 9, 1, 14, 12, 62.419. See, xy is this going to be x equals 0. It's going to be x equals 1. The whole model is written this way: B naught plus B1 x plus error. And this part is called y hat. You know that. Where y hat, sorry, not y bar, y hat is B naught plus B1 x. You can write that one in another way. You can say y hat is B naught is y bar short plus y hat, y B1 is nothing but y bar tall minus y bar short times x. See? Another way to look at it. This is not this way to look at it. Like several ways you can get this done. See? And write like that. See? See? That's that. See? That means the increment you add on the thumb length. You add on thumb length of someone in the tall group. See? This one 0 for this one. This one. Now go ahead and run Supernova to print the complete ANOVA table for height to group model. See, height to group model. You already got the height to group model. See, you get the complete ANOVA table. See, I'm gonna run Supernova of this guy. See, and this one. See, that would give you this one 11,880.211 sum of squared. Residual coming from the empty model, that's unexplained residual, the leftover residual from that empty model. This is that error being that this much of error being explained, this much of error not being explained, 11,049, large number of error not being explained. See, doesn't matter. Even, see, and this is the see how much error. See, explained by the out of total error by due to this error 830.880 divided by 11,880.211 error being explained by this model. That means almost 6% of error being explained. Variation, so much of error not being explained. See, that's another way. See, f means like these two divided by this one. Like that. This is the p value. See, the SS total, see, the total squared error of thumb length from the grand mean. We know that the remaining SS from the empty model. You can either say this is the remaining, remaining sum of squared residual remaining sum of squared residual, or the leftover sum of squared residual from the empty model. Or that's the total squared error from the thumb length from the grand mean. That's the same thing. All of the sum of squared left over from the empty model of thumb length versus the error from the empty model of thumb length. Same thing. See? What is PR in the height to group? See? PR is the proportion of variance explained by this model. You know, please, 6%. See? Like that. So now, see, let's now compare the sex model with the height to group model. Both these are two group models and both have the same outcome variable, thumb. What differ is the explanatory variable, sex and height to group. We've pasted in the supernova table for both models. Look at what happened. You can see very interesting thing. See, this is the height to group model. Height has been considered as like a categorical variable. Gender has been explained into as a categorical variable. If you go to total sum of squared, that means like an empty model, that leftover FTOV, or the sum of squared residuals, sum of squared residual not being explained by the empty model is same for both cases. See, 11,880.2. But how much being explained by this model? 1,334. This model only 830. Less. That's why this pre is less. Here pre is a little bit higher than this one. See? As we mentioned that, can you remember the cutoff value for the pre? You can remember the cutoff values for pre. By looking at the pre, you can figure out whether it's going to be medium or large. See? Pre. 0.25, see, more than 0.25, pretty large effect size. Between 0.25 and 0.09, medium effect size. Between 0.09 and 0.01, small effect size. So if you go ahead and look at this pre 0.06, that means small effect size. Look at here, more than 11, 10, 9, therefore it's a medium effect size. See? The total is the same for both models because the outcome variable is a thumb and the empty model of the thumb is the grand mean is same. So the total error from the empty model is the same. Doesn't matter. Whatever the explanatory variable you are planning to use in the very beginning, empty model involved with just a thumb length grand mean here and here. Therefore, the total sum of squared means SST means nothing but the squared deviation of the data point from the grand mean. So they both be the same. That's why they're the same. Which model explains more variation in thumb length? For sure, sex model. See, as I said over here, more variation has been explained. Or the pre is higher. See, 1300, around 1300. Here, 830 only. How can you tell which is better model? See, the meta model has a large pre. The beta model has a large sum of squared model. See, they both should be large. Sum of squared of the model, and these two should be more higher in beta model. See, compare 830 large. Sorry, I'm looking at wrong. See, large compared. See, these are large. SS. See, if you compare SS, sum of squared model, sum of squared residual, see, reduced by the model. Sum of squared residual model is reduced by the model, or sum of squared model sum of squared is high in this one. So does with the pre. So therefore this is beta model, sex model. Excuse me. How could you tell which beta? See, and the other one is beta model has a small SS, see, error left over, SS error, SS model. Look at the SS model higher, SS model higher, SS model lower. Compare these two. Residual being explained, leftover. Look at the leftover. Less leftover, higher leftover, because they're not being explained. In that sense, even this is the best. And this one, higher, lower. See, compare contrast in that way, the sex model gonna be the S model. Now, instead of going to 2, we can just divide this height into 3 groups. Revise the code below to make the new variable call the height 3 groups that divide the height into 3 groups, each with an equal number of students. Label them at 1, 2, 3 as short, medium, and tall. See, fingers, height, 3 groups now. 3 groups. Entire fingers height gonna go to 3 groups, 3. And fingers height 3 groups. Fingers height 3 groups. By default they give 1, 2, 3. We don't need 1, 2, 3. 1, 2, 3 should be labeled with short, medium, and tall. And then we're gonna write this one and then see what you get. See? Okay, height 3 groups. You have a tall, medium, like that. Tall, medium. Like that. 3 groups now. Now calculate and print out the group means of thumb length of the 3 right groups. See? Print out the group means. How do you get the group means of this one? Use the face editor to print out the group means of thumb length for the 3 right groups. See? We know how to do that. My favorite statistics. Given by okay. Thumb has been given by in terms of height 3 group. Height 3 ROUT data fingers. Height 3 favorite statistics thumb. 3 heights. Height HGIGHT 3. Favorite stats of data. Come. Okay, I'm gonna get this one. Okay, fingers. Favorite statistics of thumb in terms of height 3 groups. Fingers. Height 3 groups data. Fingers. Their minimum, see, by their category, we got the favorite statistics, see, by number summary. What is the pattern of means from favorite stat across the 3 groups? Across the 3 groups, look at the pattern. If you go mean, getting larger, see, average 56. This average is 60. This average is 64. That should be like that, see. The taller groups tend to have the longer thumbs. Taller groups tend to have the taller groups tend to have the long thumb length. These are thumb lengths, okay, thumb lengths. For the tall group, 64, the average thumb length. For the medium group, the 60 would be the thumb length, average thumb length. For the short group, 56 would be the around 56. Okay, I'm talking around 56 would be the average thumb length. Fit in the height 3 group model. Now they can fit this one into thumb length. See? Then you have height 3 groups and data fingers. Okay, now. So now this can fitting into what? New variable called now x1, x2. See, now you're gonna have another x. See, another x. You have to, since this is a 3 group, make sure you're gonna include another x value. Earlier 2 group, you have 1x. 3 groups, you have added 2 groups, see, 2 x values. And then 3 parameters, B0, B1, and B2. See, think about how this is going to work. See, think about how this is going to work. See, that's the thing. This is B0. This is B1, X1. See, B1. See. So how this can be interpreted? Okay, let's say how this can be interpreted in this situation. This is your B0. This is your B1. This is your B2. See, B1, B0, B2. What do the variable represent? Okay, X, Y, the individual thumb length. X, whether the individual is in the medium group. X1 means whether it's in the medium group, whether the individual is in the tall group. See, look at how this has been set up now. It's not with respect to short group. You're going to go ahead and start from the top. See, tall group, whether the individual is in the tall group, X. See, this means whether this person is in the medium group. The short group has not been included. So earlier, I'm going to compare this one with what we had earlier. Okay, I'm going to do some kind of when you have this one, 2 group. If you have a 2 group model, okay, you have a thumb length, okay, then you have a what, height, 2 group plus area, or residual. So this is Y. If I'm going to write mathematically, this is Y. This is B0 plus B1 X plus C. See? So the B1 means what? X. X here means what? And here X means what? Okay? So they were asking X1 and X2. So here X means what? Okay. X means where X means whether the individual in short or whether individual is in the short group or tall group. That's what we want to know. See? The tall group, whether tall group, okay? If it is in tall group, X equals 1, tall, see? If not, X equals to 0 means short group. That's how your short comes into the picture. That's how you're going to assign X1 and X2. Your question should be whether X is whether the individual is in tall group. Okay, not the short group, tall group. If it is that X, you put the X plus 1. See, that's the idea over there. But when you have that, see, 3 group model, 3 model, again you have a thumb. See, now you have a height, 3 group plus residual. See, plus residual. Okay. Then if you write this one, Y equals B0 plus B1 X1 plus B2 X2 plus E. X1 means whether the individual is in medium group. That means X1 equals 1. X2 means what? See? If not, x1 equals 0 means what? x1 is 0 doesn't mean that they were in the short group or tall group. We don't know. We come back to this one. Then it should be in the short or tall group. For sure, when x1 equals 1, we know that they are in, see, medium. Medium for sure. In the similar fashion that x2 I'm going to write on the other side, okay? x2 means whether the individual is in tall group, tall group. That means x2 equals 1, tall group. But x2 equals 0 means whether he's in maybe short group or medium group. Don't know. See? That's the idea. That's what they say here. See? That's what they say. See? The individual thumb length. This the individual is in the medium group. X1, tall group. Okay. So how do you code this one? See? You need a code. See? This is the important part. So if it is in short group, in both ways, see? If it is in short, x1 has to be 0. See? Short means x1 has to be 0. x2 also has to be 0. See? Short. If you are in short, 0, 0. Both x1 and x2 should be 0. If medium, definitely x1 is 1. The rest would be we don't know. I'm going to put 0. x1 is 0. x1, x2 is 0. See? x1 is 0, x2 0. We don't know whether it's in which group, whether here or here, we don't know. See? See? Whether in short group or that one, we don't know. Then go to the tall group. Tall group means x2 should be 1. X should be 2 will be 1. If it is 0, we don't know whether x2 we should be 1. If this is 0, I don't know whether it's in this group or that group. See? This is the code. See? So if somebody in a short group, this simply means x1 0 and x2 also 0. Medium group means x1 1, x1 1, x2 0. And tall group means we have 0 and 1. See, that's all that we focus one at a time. If it is tall, see, if it is tall, see, if we combine now everything that I wrote over here on this book, short means you have an equation v0 plus v1 times x1 equals 0 plus v2 times, okay, times x2 equals 0 2. If it is in medium group, y equals b0 plus b1 times x1 equals 1 plus b2 times x2 equals 0. And if you are in a tall group, y equals b0 plus b1 x1 equals 0 plus b2 x2 equals 1. That's the idea. That's how it's been coded. Look at short 0 0, 1 0 0 1, 0 0 1 0 0 1. See? See? Right there. So if you go back to here and interpret But the value B0 is the mean of the short group. B1 is the increment you have to add to the short group to get the mean of the medium group. See, it is the increment you have to add to the short group to get the mean of the medium group. So this means if I'm going to draw this one, this time, so you have a thumb length here, thumb is y is a quantitative variable. See, then you have a x is here height 3 group, which is categorical. So you have a short, you have a medium, you have a tall group. Then you have a something like this, and something like this, something like this. So you have B0, it's nothing but y bar of the short people. And then you go straight to the this one, that is y bar medium. See, then this is called B1. B1 is how much you have to add to the thumb length, average thumb length of the short people to get the average thumb length of the, see, average thumb length, see, have to, the amount increment you have to add to the short group to get the mean of the medium group. And B2 is the increment you have to add to the short group to get the mean of the tall group. So B2 is, if you go ahead and see, from here to here, you have y bar tall means this is B2. See, that's the increment of thumb length. See, increment. See, to get the mean of the tall group. Increment you have to add to the short group to get the mean of the tall group. See, add the short group to get the mean of the medium group. Right there. We can substitute in the parameter estimate in the model like that. Then you have this guy, you have this guy, you have that guy. So as I said that if you want short, so this one, see, short people, see, then you go ahead and then write this down, the model. Okay, I'm gonna write down. So y equals, see, B0 plus B1x plus B2x. Okay, let's say y hat, this is y. Okay, B0 plus B1x 1 plus B2x2 plus e. I'm gonna consider only this part. Y hat means like a B0 plus B1x and B2x2. See, B2x2. So I can say y hat because B0 is nothing but 56. Okay, if you want, you can get that one. 56.07 plus 4.15 x1 plus 8.02 x2. So for short, see, for short group, y hat for short group is 56.07 plus 4.150 plus 8.020. See, x1 and x2 both 0. So it's going to be nothing but 56.07, which is B0. See, that's y bar, y hat for that guy. The same as the y bar of short people. See, then I need a y bar, y hat. Then I need a for medium group. For medium group, you need the y hat for medium. We have B0 plus B0 is, which is 56.07 plus and 4.15 times 1 plus 8.02 times 0, 8.02 times 0. So 56.07 plus 4.15, which is 22. 0, 60 point. This one is nothing but y bar of the medium. See, y bar hat. See. Then for tall group, y hat t equals 56.07 plus 4.150 plus 8.07 times 1. See? So 56.07 plus 8.02. So then 0.94 64 by hat t is nothing but y bar tall. See, y bar tall, medium average, tall average, and short average. See? The averages are 56.07. See? So this one is 56.07. This one is 60.22. B1 is 4.15. B2 is 8.02. Y bar T is 64.09. See, I located pretty much everything on this picture. See, this is B naught, which is Y bar short. This is B1, 4.15, being added to this one. So that's 60.22 for the medium group, average thumb length. And I added point B2 from here, okay, from the short people. See. So like that, and then 8.02, then it's going to be 60. So that's why they say, what's the difference between the parameter and a variable? Parameters are fit from the data. See, parameters are fit from the data. The values of the variable are part of the data. You have to be very careful. Parameters are fit. Parameters are fit. These are parameters. It's not a part of the data. The variables are part of the data. See, it's part of the data. This is part of the data, x1 and x2, part of the data. See, but these are fitted by the data. That's what they say. That's very clear. Parameters are fit from the data. Values of the variables are part of the data. Each person thumb length is composed of the same parameter and different value for the variable. See, everybody's the thumb length is going to change, not because of the parameter. Parameter already fixed. The gaps. Average, see, the gap between the average heights, thumb lengths between medium group and the short group, the tall group and the short group. And so does with the medium group and the short group. See, the gaps are fixed. They've been already evaluated by the data. It is evaluated by the data. It's not a part of the data. See? That's another way to look at it. The variable have a sub-I to indicate that this value vary from person to person. Parameter do not. These parameters values are, see, fixed from person to person. Here, that's why they put I here and I for this guy and this guy to indicate those are for individuals. So that from variables going to change from individual to individual. See. So this is one. Let's work out equation. Someone in short group, we already did that one. See, 56 point. Someone in medium group, we did that one already. See, 56.4 point. And tall group, if you want. See. Look at the averages. And if you go ahead and check that averages from the favorite statistics, you can easily say tall group 64.09, short group 60.22, sorry, medium group 60.22, 56.2. I think that's the same value we got it from another way by running the favorite statistics. That's the code talk about. And then let's check that the three group, let's fit to this one and get this model. See, still the same. That sum of square total would be the same. I'm gonna call this one. Okay, this one. So let's run the supernova on height 3 group. See, supernova. See, sum of square total. So now you can compare with the two group model and this one, and then you know how to do the total has been that. The empty model, unexplained 11,880 sum of square residuals. But if you go to three group model, they explain 1,690 residuals being explained, and the more explanation, see, is higher than this one. And even this one 40, this one 6%. Then unexplained, this one larger, this one smaller. In that way, this is the best group. See, look at the ANOVA table. What proportion of variation thumb length is explained by this model? Height 3 groups. See what explains. See 3.14. See that much of variation has been explained by this 3 group model. Compare the ANOVA table and think what is the total same for the both models. Both models sum of square total SST being the same SST, not SS residual, not SSR, not SSM. SS total being the same. Which model is better fit? 3 group model. See? How can you tell which model is better? See, the beta model has a large pre, the beta model has larger sum of square residual, beta model has a smaller leftover. See? SS model, sum of square residual for the model. See? So you have like error being reduced, that means this minus that would give you this. See? Residual. Larger residual not being explained. See, larger residual SSR, large. See, small. This has to be leftover. Has to be smaller. This one is smaller compared to this one. This one, see, 11,000, and this value sum of squared model. See, being compared and contrasted. That means in both cases, to compare and contrast, these are the ones that you have to look in. Okay. So comparison of model of CAT model. Okay, I'm gonna say like that. You're looking into the pre, see, and you're looking into the SSM. You're looking into the SSR. So for this one, two group model. Here, 3 group model, 3 group model. Okay. So if you look at the pre, see 0.06. I'm gonna go to 0.07. This one almost 14. 3 group, and sum of squared model 3 group 1690, around 1690. This one 830. Okay, around. Okay, approximately. This one approximately. approximately residual. See, this one has a 10, 189. This one has 11 or 49. See. So we get higher, go up, let's go down. These are up, it's down, it's down, it's up. So therefore, this is the best model. See, less residuals, left over, 10,000, 11,000 left over. How much been explained? 1690. How much been explained? 830. Less been explained. How much the proportion wise? How much been explained? 14% been explained. That carried from the empty model. See, like that. See. Compare this one and both models. Why is the total of sum of square the same for both? See, we talk about that one. See, this model produced the more accurate prediction, thus reducing the residuals. See? The better model has a smaller one, and this one. See? Improving model by adding parameters. See? You can add in parameters. See? How come you're gonna improve model? See, look at what happened. You probably noticed that the previous section that the 3-parameter height 3-group model explained more variation than the height 2-group model. That is, it reduced the unexplained error more than the height 2-group model when compared with the empty model. See? If we look at the histogram and jitter plot for the 2-group model and the 3-group model below, you can get a sense of why this is. By adding more categories for the height, we are able to reduce the error variation around the mean height for each group. Look at the 2-group model. Look at their histogram. Look at the thumb length for the short people, tall people, thumb length. Okay, look at their jitter plot, short, height 2 groups. Look at the gap. If you go to this one, these are the histogram. See, and this is the way how it's been in jitter plots. In general, the more parameters we add to model, the less leftover error there is after subtracting out the model. See, leftover error getting less and less and less. That is the more variable being added to more parameters being added to the model, because we have said many times that the goal of this is to reduce the error. This seems like a good thing, and it is, but only to a point. See? Let's do the little thought experiment. You know already that the 3-group model explained more variation than the 2-group model. The 4-group model would explain more than the 3-group model, and so on. What would happen if we kept splitting into more groups until each person was in their own group? See? If each person was in their own group, the error would be reduced to 0. Why? Because each person would have their own parameter in the model. If each person had their own parameter, then the predicted score of the person would just be the person's actual score. And there would be no residual between the predicted and the actual score. See? There's no error, because that everybody be in that group into their own group. Each one will have one group. Each one. There are two problems with this. First, remember that our goal is to model and understand the data generating process. So even if we fit our data perfectly with our model, it would not cover all the people who are not in our sample. Second part, understanding simplifying. If you have many parameters as we have people, we haven't simplified anything. In fact, we have introduced a lot of complexity. That means that if you are planning to that, just rather than dealing with the model and then rather than summarizing and get the summary and then work with that one, if you simply work with all the individual that separate scores, what's the point of having a model? Model pretty much gonna do, rather than working with the individual scores, they're going to fit that one into like some kind of a reasonable structure in which that we can easily use the summary statistics to talk about that one in that reduced form. So then if you are trying to just simply say that for each and individual, if you are trying to have like a group for each and every individual in that one, that would add up so much of complexity. So that is a problem. So that's not going to work like that. And on the other hand, we don't know how the population from which this data are coming from look like. We don't know. So although we can improve model fit by adding parameters to model, there's always a trade-off involved between the reducing error by adding parameters to model on one hand, and increasing the intelligibility, simplicity, and elegance of the model on the other hand. So that's why we have to be careful. So the more variables, more parameters you added to the model, far unstable that your model would be. That's why we have to have a trade-off. We have to have a balance. You are not just throw the parameters for the sake of throwing the parameters and say to try to come up with some kind of a model and thinking that, oh, I fitted this into certain model. It's not going to work like that, because of that when we come to the statistics, you have to make sure you have to minimize the parameters plus get a very elegant, very reliable and simple model that would explain pretty much everything, rather than that simply throw in and say, okay, I'm going to divide this into 4 groups, 5 groups, 6 groups, 7 groups, 8 groups, 9 groups, 10 groups. No, you cannot do like that. So that's why we have to have a kind of like a way of doing this one. That's why they say that there's a limitation of pre as a measure of our success. See, there's the pre. If we get a pre of 0.40, for example, that would be quite an accomplishment. We had only added a single parameter to the model. But if we had achieved that level by adding 10 parameters to the model, well, it's just not as impressive. Statisticians sometimes call the overfitting. See, overfitting. You can see. If you add 4 parameters and try to get the same value, it's overfitting. There's a quote attribute to Einstein that sum up things pretty well. Everything should be made as simple as possible, but not simpler. A certain amount of complexity is required in our model, just because of complexity in the world. But if we can simplify our model so as to help us make sense of complexity and make predictions that are good enough, that is good thing. See? That's how the Einstein is telling. Everything should be made as simple as possible, but not simpler. You cannot go to the simplest version. A certain amount of complexity is required in our models, just because of complexity in the model world. Because of the complexity in the world, you really need some kind of a complexity inside the model. But if we can simplify our models in such a way to help us to make sense of complexity, or that we can understand the complexity and make predictions that are good enough, that's a good model. Okay? So that means there's a trade-off between that, not to make that the model complex by just simply throwing or that dividing all the data, factoring the data into as many groups as you want. No, you cannot do like that. There's a trade-off. Okay? The goal of making statistical model isn't just to reduce error. No, we want to reduce the error, sure, but we are other goals to keep in mind when built in the model. See. But it's as in beginning that we had some kind of a discussion, some kind of a notion. We thought that we are statisticians are supposed to reduce the error, but it's not enough. It is not what we are doing in statistics. There are other goals to be achieved in this statistical analysis as well. See, so what are they? So the model help us understand something about the DGP. Yeah, you have to build up a certain model to understand something about your population. The model help us make good enough prediction as well too. And the model balances simplicity and accuracy. See, model should be simple but accurate. In that sense, all this will be taken into account when you are building up a model. Okay, what is the worst thing about pre? The pre does not tell us how much error has been reduced relative to how much complexity has been added to the model. they're going to talk about how much the error has been reduced, but at the same time, they're not going to talk about that how much complexity that you have added while you are reducing the error. So that's the worst part of that pre. Pre simply say that, okay, how much error being reduced, but that doesn't never mention that about how much, at the same time, how much complexity has been added to the model. So therefore, there's some kind of a worst thing about the pre as well. So therefore, the pre is not enough for you to make a conclusion. That's why we're going to jump into the another kind of a quantity called the F ratio. That F is nothing but, you know that F is nothing but the ratio between the mean squared model divided by the mean squared error, which is this one. See? So that's why they are trying to explain. Pre alone, therefore, is not sufficient guide in our quest for reduced error. Yes, it tells us whether we are reducing error, but it does not take into account the cost of the reduction. Just as the sum of squared needed to be divided by n minus 1 degrees in order to get a comparable measure of variation, we need a way to correct the pre so as to take into account the number of parameters it took to realize the gains in pre. Pre is not enough for you to that. In the pre that you simply take into account the sum of squared only. They say sum of squared are not only taken into account enough, then sum of squared should be divided by their own degrees of freedom to that get the averages. See, like this average, this average. See, that's why. Let's go back to our analysis of variation table printed below and focus on the three columns that come between SS and pre, DEF, MS, and F. Just a note, DEF stand for the degrees of freedom, MS stand for the mean squared, and F, they stand for the F ratio. See, we know this one. We were talking about this one. If you take the SS divided by the degrees of freedom, which n minus 1 the empty model, you end up with the mean squared. We know that, and this divided by that will give you the mean squared error model. This divided by sum of squared residual divided by the degrees of freedom of residual would give you the mean squared residual. Total sum of squared divided by its own degrees of freedom would give you the total sum, mean squared total. See, like that. Try out. We were written the code to calculate the variance of thumb length using the function var. Use R as a calculator and try to take the sum of squared for the empty model and divide it by the degrees of freedom and see what's going to happen. Look at this var. Try to take in SS from the empty model and dividing it by the degrees of freedom. You can get these numbers from the supernova table. The empty model is loaded. See, so what they say the SS from the empty model and dividing it by degrees of freedom. See, and the empty model. Get this. Wow, thumb length. Wow. Yeah, that's nothing but this 76.155. See, same thing. See, 155. So this is very interesting. So if you take the square root on this one, okay, I'm gonna get the square root on this one. So SQRT of 76.1552. Is something. Okay, so me see. If you take the SS and divide by the degrees of freedom, this one, and end up with the mean square, see, or the variance of this one, see. If you take the SS and divide it by, see, divided by the degrees of freedom, which is n minus 1. See? Mean squared, this would give you the s squared. See? Y minus y bar squared divided by n minus 1 would give you this one. See? Partition in degrees of freedom, we have done that one. Okay. I had to come to this one. Before that one, can you remember at a certain point, we had something, I want to get back to something we were discussing at a certain point. Cohen's D. I want to go back to Cohen's D. See, can you remember Cohen's D over here? See? Yes. They say that the best estimate, see, solution is this one. Now, the way to find the pool standard deviation is simply take the square root of mean square error. See? Look at this one. Look at this one. Look at this S. Look at this S. See? See? Standard deviation. They say the standard deviation, this one. This standard deviation can be whose standard deviation? Look at here, there. See, if you try to calculate the Cohen's D, you will soon encounter a question: which standard deviation should you use? Okay, the standard deviation of the outcome variable for the whole sample, or the standard deviation of the outcome variable within the groups. If the group means are far apart, the standard deviation of the whole sample might be considerably larger than the standard deviation within each of group. In general, we use the standard deviation within groups when calculating Cohen's D, because this is our best estimate of the variation in outcome that is not accounted for by our model. But because the standard deviation will often differ from group to group, we need a way to combine these two deviations. Normally, we're going to utilize this ones that it's best estimate to get the pool one. So that if you go ahead and calculate this pool one is same as the root mean squared error, MSE error. Now, this is what I'm talking about. Follow very carefully. See? Look at this one. This pool one is nothing but root mean squared. Root mean squared error. But if you really want to find the standard deviation of y, it's root mean square total. That's what I want to make clear here. That's what they were telling you. Okay. Look at what's going on over here. Okay, I'm gonna go back to where I was a few minutes ago on F. Okay. Next one. Okay. This is what I'm talking about. You found variance this much. Okay. Okay, now the same thing, instead of that one, I'm gonna write the SD of that guy. Okay, fingers, go to fingers, go to thumb. I'm gonna get the standard deviation as well, 8.72. Look at, I'm gonna get the standard deviation not from the RMSE. I'm gonna go to the total sum of square. SST is nothing but root mean square total. See? Root mean square total is square root of your total. See? 76.155. See? So our root mean square total will give you same answer. So this is very interesting. You have a root mean squared error, which is a standard deviation as well. That's a pool standard deviation. We have a root mean squared error, root mean squared error based on, see, it's a two-group model. Two-group model, doesn't matter. Pool standard deviation. If you need the pool standard deviation, this is what I'm trying to say. If you need the pool standard deviation, it's nothing but the square root of this guy. If you need the standard deviation of whole thumb length, that would be this guy. That's what I want to tell you. See, this is what I'm trying to explain over here. Okay, I'm gonna try to explain this one. This is what I'm gonna try to explain. I'm talking about standard deviation. Okay, standard deviation. Okay, so under this one, I have something called pooled standard deviation, which is S pooled. You know how to calculate. You know how to calculate. It's nothing but degrees of freedom of male, first group, standard deviation of male, plus degrees of freedom of female, standard deviation female, divided by degrees of freedom of male, plus degrees of freedom of female. They say this is same as the mean squared error and square root, which I'm going to call that one root mean squared error. That means in this case, it's going to be how much? 71.286 square root. See? 71.286. I'm talking about height 2 group. Okay? 71.286 square root. 71.286. 286. See, 286. That's the pool one. Okay, that's the pool. That's the pool standard deviation. That's a one set. Second one is a standard deviation of thumb length, which is S. They say it is nothing but, if you want to find, how do you find? You go to some y minus y bar square divided by n minus 1. This is same as mean squared total, and take the square root. Or you can say root mean squared total. As a number, you can say that's 76.155. See, this is what I'm trying to explain. You know the same. See, 76.155. So you have a pool standard deviation. You have a standard deviation of thumb length. Look at, they both are coming from the ANOVA table easily. One coming from root mean squared. The other one is root mean squared total. See? Look at. That's why they were trying to explain here. That's why I was doing this one. Then if you want pool, see, root mean squared total is the pool one. See, so they were trying to say that this guy square root is, or this guy is same as the variance. See, it's the same thing. See, the same thing. Then partition in degrees of freedom. See, you can remember the how do they partition? See, model. This means like a degrees of freedom. How they model partitioning. You can remember the partitioning of degrees of freedom very easily. We had a set up. I'm gonna focus only on the degrees of freedom. Then this is my model. This is my error. This is my total. Okay. This is nothing but number of x. This is nothing but n minus number of parameters. This is nothing but n minus number of x. So this one is now the two group model. Okay, two group model which is y equals b naught plus b1 x plus e. Number of x, see, 1, n minus number of parameters, see, 2. So this one, n minus 1. See, okay. So in that particular example, I show you how this is gonna be. There we have like 157, okay? So this one is 1. This one is 157 minus 2, which is 155. 157 minus 1, which is 156. So in another way, 1 plus 155 is 156. It's the general formula, number of x, two group model. It's a similar fashion. Let's go to three group model. Three group model. So you have a here model, error, total. So the degrees of freedom is n minus number of x. Three group model y equals b naught plus b1 x1 plus b2 x2 plus e. So 157, we have n minus, there are two x values, so therefore this is going to be 155. This is going to be n minus number of parameters. So you have 157, number of parameters 3, so 150. Sorry, not this one, not number of x only. Number of x. Number of x. Number of x. Number of x, which is 2. Okay. Which is 2. Number of x2. Okay. Then this one, number of parameters 157 minus this one. Total is nothing but n minus number of x. N is 157. Number of x is 3. Number of x is 2. Sorry, number of x is 2. 150. 155. 57 minus 54. Okay, number of x 1, number of n minus number of parameters 1, 2, 3, 154. Not this one. Number of x. You see how much they have in that one. 3 group. 3 group. X model. This one, right? 2 groups. Yeah, this one. This one, yeah. 2, 154. is this? 154. 57. Okay, sorry. It's a number of this one always 1. We can make it 1. This always 1. N minus 1. N minus 1. This one. Okay. So always N minus 1. We don't need to put the number of x. Okay. Always N minus 1. So okay. N minus 1. N minus 1, which is 1, which is 156. See? Now it's right. This one equals 1 equals N 157 minus 1, which is 156. See? Not based on the number of parameters, they get cancelled off. Later on, we left over with N minus 1. The leftover going to go to that one. Always N minus 1. See, that's how you're going to get the decrease. Here, number of x. Here, N minus number of parameters. This is N minus 1 always. Always N minus 1. Okay. So that's what how they were talking about the degrees of freedom, partition of degrees of freedom. See, they were talking about that one. See. Then varieties of mean squared. See, mean squared, we talk about that one. Large scale, so mean squared is this divided by this averages. See, we talk about that. Okay. See, these are the 3 varieties of mean squared. Talk about that. Then mean squared error is sum of squared error divided by degrees of freedom of error. We know this one. And mean squared total is sum of squared. See, mean squared total is sum of squared model divided by degrees of model. And sum of squared model total, if you want, we don't that much pay attention for that one. Okay. So then these two divided by that one is nothing but mean squared error divided by this one. You see, like this, that's F ratio. We talk about that large scale. This divided by mean squared model divided by mean squared error is F ratio. See. So that what that means, the variance explained by the model is 11.66 times larger compared to the leftover variance unexplained by the model. See, explained to unexplained. This one what? Explained to total. Total leftover coming from the empty model. Last time, see, pre means like a how much being explained, how much being explained, how much explained by the model, how much sum of squared residual, sum of squared, yeah, residuals explained by the model that been left over, that's been unattended, that's not been explained by the using the empty model. But this time we say we're not gonna take into account the empty model. We're gonna say that within this one, how much been explained with respect to unexplained within the model, how much explained, see how much variation have been explained compared to the leftover variance unexplained by the see. This is if this not been explained by this particular model, not the empty model. This particular model, how much been left over, see? This much. Compared to this leftover, if the leftover compared to leftover, the explained one is higher, see, 11 point something. It's good, see. That's why they say 11% of, see, 11%. If you have 100, see, this divided by this one, see, 11, see, like a percentage is a way high, more than that, see, 11 times better, see, 11 times better. As a percentage, it's going to be 116, see, 1065, see, percentage if you want to multiply by d divided by 100. So like that, see. So if you keep this one, how much that, how multiple in terms of see how much time, the larger compared to the leftover variance unexplained by the model. See, this is not explained, but the explained more part is way high, 11 times. So if you took another sample of 157 students and asked them the measurement of thumb and height, would we get the same F ratio? No, no. We're going to talk about that in next class. No, it's unlikely. What is the F ratio? It's a statistic. It's a statistic. Why would we unlikely to get the same? Because of that F ratio statistics, just like the mean pre, a different sample will result in different statistics. Okay? And then if you get another one, another sample of the same sample size of 157, and then calculate, you're going to get different this one, different this one. All these going to change. That's why those are called statistics. Okay. So I explained this one. So I think we did this one in the beginning, that F can be explained even in the terms of pre. See, we need both these formula because they give us a different values of the statistics. Continue the equation. The pre explained by additional parameters is not very special because it's about the same as the average amount of pre that could have been explained by another parameter. See, that's pretty much the same thing. If the F ratio is 1, F is 1 means like a what? F is same, that they say explained by our additional parameter is not very special because that if you get the 1 for this one, what's the point of that? Means that it's not been introducing a new variable, new parameter would not contribute to explain the variation in y. So that would be not a good way of doing that one. So that's the kind of a like idea that if you get a 0, or this one 0, see, can we get the 0 for this one? 0 means like there's no point of that adding anything like that. But if you get the F ratios 1, F is 1 means like nothing has been explained by the new variable. So there's no point of that adding a new variable. But if you get, as in this example, that 11 times, see 11 times larger, that unexplained variation with respect to the unexplained variation within this model is 11 times larger. So therefore, this is a good model. So that's the end of this chapter. I hope that you will learn and then you enjoy this class, and then this is the end of our semester. Plus that your final exam going to be based on the chapter 7. These questions, okay? Chapter 7 review questions. Just do this set of questions for your final exam, and then you still have a time until Thursday. I hope that all you guys have already signed up for the next class, in which we're going to talk about the analytics. Our next class, analytic models. Okay, and what's the next class? Next class is, I think, let's see. We have a 605. Okay, 605. 605. So this 605. Let's see. Okay. Oh. Yeah, let me see. Something is not working. Yeah. So I think in next class, see, yeah, as I said, the analytic models and the data system. In that one, we're gonna see you guys on Monday. Everybody has signed up for that class, and then until then, just go ahead and then finish your get all the homework, quizzes, midterm, final exam for this NR 600 class, and then you still have a time until next Wednesday. Okay, next Wednesday, and then. So until then, that I'm gonna wish you that very good luck, and then you guys have a nice weekend, and then see you guys tomorrow at pretty much the same time. Okay, thank you, bye bye, take care.